So what we're going to look at next here is implicit differentiation. And that, the word implicit here refers to the idea of an implicit function. Where when we see the variable y, we believe that it is a function of x. And so the idea of an implicit function is the variable y isn't just a variable, y is a function of x. All right, so a simple example of that is if we say y, let's see. Yeah, let's do this. Y equals the square root of x. We know we can apply a little algebra and get the inverse function here, which is x equals y squared. And then, like you can, when you solve an equation, you can take the square root of both sides, you can multiply by the same number on both sides, you can add the same number on both sides. It turns out that you can differentiate on both sides of an equation and the equation will stay true. So, just like multiplying number on both sides, or taking the square root of both sides of an equation, we can also differentiate. And we can do that as long as we realize that if we see a y, we have to assume it's a function of x. And if we do that, that means the chain rule is going to get involved. So for example, let's take this one right here, x equals y squared. So what I can do with this is I can differentiate both sides. So take the derivative of the left side, and that should be equal to the derivative of the right side. Okay, so if x really does equal y squared, then the derivative of x should really equal the derivative of y squared. That's the idea of implicit differentiation. You can differentiate on both sides and keep the equal sign. Now, the catch is that the y here is actually a function of x, which means the chain rule is involved. Now, on the left side, the derivative of x with respect to x, that's just 1. That's pretty easy. On the other side, I have the chain rule involved. So the derivative of y squared, the derivative of something to the second power, is 2 times that thing to the first power. And first power is kind of boring, so we can just get rid of it. The chain rule says, though, if the inner thing is more than just an x, and that is more than an x, it's a function of x, then I have to multiply by its derivative. So that would be y prime. All right, so I've taken this x equals y squared, I differentiated both sides, I get this new equation here. And so I'm just going to fiddle with it in a minute. I'm going to solve for y prime. So if I solve for y prime, I would have to divide by 2y. So that means y prime is equal to 1 over 2y. Right? Now, what is y again? Well, up here, y is the square root of x. So that means I have 1 over twice the square root of x. And we learned before that the derivative of the square root is 1 over twice the square root of x. So it turns out I can use implicit differentiation to deal with inverse functions because of this chain rule applying to this implicit function y, which means I see a y, but I really know it's a function of x. That's basically what the implicit part means. And then the other thing is I can differentiate on both sides, provided the original things were equal, the derivative should be equal, okay? So where this becomes more useful is with equations where I can't easily solve for y, or it's better not to. Okay, so the simplest example is the unit circle. encounter one in a minute. So the unit circle equation is x squared plus y squared is equal to 1. Now we could solve for y, right? And if we do that, we would subtract the x squared over, so we get y squared equals 1 minus x squared. Then we take the square root of both sides, so y would be plus or minus the square root of 1 minus x squared. And this plus or minus a problem because it's an or. For any x value I plug in, I'm going to get two different y values. So this thing is not a function, right? And like we know, the unit circle ain't a function. Because it fails the vertical line test at almost every point in its domain, except at the endpoints here. All right, so this is not a function. However, we can express this object here, this circle, with a single equation, even though it's not a function. Over here, this is actually two functions. It's like function 1 is the upper part, y minus x squared, and function 2 is the lower part, is the negative of the square root of 1 minus x squared. Okay, so I have the top half and I have the bottom half. So rather than dealing with two different equations, it turns out we can apply calculus to this single equation here by using the implicit function theorem. So I want to look at slopes on the unit circle. And to do that, I have to find dy dx, right? Slope is change in y over change in x. So I need to know what is dy dx. And I can just differentiate this equation as I see it. So I can take the derivative with respect to x of this left side, x squared plus y squared, equals the derivative with respect to x of 1. So let's do the right side first. That's easy. The derivative of a constant is 0. On the other side, we have a rule that says we can slide the derivative through the sum. So we can take the derivative with respect to x of x squared, which is just 2x. We can take the derivative with respect to x of y squared, which at first glance is 2y, but y is a function of x here. So then the chain rule says, whoa, 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 y is a function of x. It's implicitly a function. Right? It's in its nature, so you have to multiply by y's derivative, which is just y prime. Okay? So that's the implicit function idea, that if you see a y, you've got to realize that y is a function of x. And if you take the derivative of something with a y, because it's not just an x, chain rule says, hey, if that's not just an x, you've got to multiply by its derivative. Chain rule says. Now we can solve y prime, because y prime is dy dx. Right? And dy dx is slope. Change in y over change in x. So I would subtract the 2x to the other side. So I'm going to get 2y y prime is equal to negative 2x. A question in this chat says, can you also put a dot above the y to mean the same thing? Sort of. People do that a lot, but technically y prime means the derivative of y with respect to x, and y dot means the derivative of y with respect to t for time. So the dot is usually reserved for t for time. And so I usually only use the dot notation if I know my independent variable means time. Otherwise, I use a y prime, which usually means dy dx. So here I wouldn't use the dot, but some people do. Technically, it's supposed to be a derivative with respect to time. All right, so that's a good question. Let me see, subtract the 2x, and then I'm trying to get y prime alone, so I divide by 2y. So now I've got that y prime is equal to negative 2x over 2y, which cleans up to be the opposite of x over y. So at any point, this is the claim now, at any point on the unit circle, the slope is the opposite of the x value over the y value. All right, let's test that out. So I'm going to pick a point on the circle. I'm going to try to draw a slightly better circle. I don't think I'm going to do very good at that today, but I guess I should have a more positive attitude, eh? So let's see. 1, 2. Suppose I put 1 right there. And 1. Did I go too far? 1, 2, 3, 4, 5. Okay. So let's see. This is my circle then. Make a circle by making a bunch of quarter circles. Hey, that's not too bad. And then the point I want to mess with here, how about x is 0.8 and y would be 0.6. So that's this point right here. And so that as a fraction, let's see, y is 3/5 and x is 4/5. So I'm thinking of like a 3, 4, 5 triangle to get that point, or you could call it 0.6, 0.8. So this is on my circle there, and I believe the slope at that point m, according to my calculation, is the opposite of the x value divided by the y value. So let's see, what's my x value here? It's 3/5 divided by the y value, which is, oh, did I write those backwards? Oh, I wrote those backwards. Oops. Well, that point's on the graph too, but it's not in that spot, it's over here. So I'll just switch points. All right, sorry about that. So here is 4/5 and here is 3/5. Okay, so let me see. Opposite of x over y, 4/5. And since I'm dividing top and bottom by fifths, I could, multiply that out. So it looks like the slope is -3/4 or -0.75. So point slope formula says y minus y1, which is 4/5, 4.8, is equal to the slope, -3/4 times x minus 3/5. So let's see if that's really true. Let's see, does it look right? Well, let's see, to get to this point right here, let's see, from this point, I want to drop 3, 1, 2, 3, and run 4, 1, 2, 3, 4. So that's where it would go there. And I could go the other way, go up 1, 2, 3, over 1, 2, oops, I lost track. 1, 2, 3, 4, over there. So that should be 3 points on the tangent line. Does that look like it might be a tangent line? My drawing's a little squiggly, but it could be. A note here, which is kind of interesting, is that from the origin to that point, that line should be perpendicular. Tangents on a circle are perpendicular to the radius there, and those look pretty perpendicular. Right? And this one right here goes up 4, right 3, and so the green slope is 4, oops. And the green slope, m, is 4/3, and the red slope, m, is -3/4. And hopefully you remember that perpendicular lines, their slopes are negative reciprocals of each other, which I definitely see there. So I'm going to have Desmos do a better graph of this than I just did. And this should work just fine. I really don't want to delete all this beautiful stuff. Just turn it off. Goodbye. And so unit circle, x squared plus y squared equals 1. And then I think that at the points 0.6, 0.8 there, I have a tangent line that is y minus 0.8. That's equal to negative 0.75 times x minus 0.6. Bang, nailed it. Thank you. So that's kind of neat. And think about this for a second, though. If we look back at our work here, the alternative to finding the derivative is to take the derivative of this thing right here, which we could do. That would involve the chain rule. So if I were to try that to see how it compares to that, that's kind of a nice, beautiful, simple formula. I love that. The derivative of y1 with respect to x, according to the chain rule, the outer function is the square root, and the derivative of a square root is 1 over twice the square root of whatever's inside, and what's inside is 1 minus x squared. Then the chain rule says you got to multiply by the derivative of the inner function, and the inner function is 1 minus x squared. So the derivative of that right there is derivative of 1 is 0 minus 2x. So I get what? Negative 2x over twice the square root of 1 minus x squared. The 2's divide out, so I get color negative x over the square root of 1 minus x squared. And that square root of 1 minus x squared, that is my y value. So it turns out that does say, oh yeah, that's negative x over y also. So we have options. Now in this case, we could solve for y and do it in pieces with the chain rule, but you can't always do that. So I'm going to show you another cute equation. Let's go over to Desmos. Let's actually bring up a new Desmos graph because I got too much going on in that one. Desmos calculator. And the expression I want to look at is x raised to the third power plus y raised to the third power equals 6xy. Isn't that beautiful? Ooh, that is called the Folium of Descartes, and it is such a beautiful curve. So what I want to do is I want to pick a point on this. Now, there is a cubic formula, but it's way harder than the quadratic formula. You could look it up if you want. I'm definitely not going over it. It's not covered in most algebra classes, but it is a thing. I'm going to pick the point, and I had to work a little bit to find this point on the graph, a little harder than I did on the circle. The point 4/3, 8/3 ought to be on this graph. There it is, yep. Okay, so that's on there. So what I want to do is I want to find the tangent line at the point 4/3, 8/3 of this Folium of Descartes here. Okay. And this is just one version of the Folium. You can have different numbers out front here, give you a slightly different looking Folium. Like if I type x raised to the third plus y raised to the third equals, how about 12x y, right? So I get a slightly bigger loopy thing, but it's got the same general shape. Kind of cute. Oops, I deleted too much stuff. All right, so now we got a little bit of work to do, so let's go to the notebook and find ourselves a derivative. So the expression that we're going to play with is x cubed plus y cubed equals 6xy. And we can't easily solve for y here, okay? Because there's a y on this side, there's a y on that side, and the cubic formula is kind of a mess. So I'm going to use implicit differentiation. So if I want to find the slope on this, that means I need to find dy dx. Dy dx is what we also call y prime. And so that means I need to differentiate. So I need to take the derivative with respect to x of this right side, and I need to take the derivative with respect to x of the left side. And implicit differentiation says we can do that as long as we realize that y is a function of x, and that sometimes we need to find y prime also, which is going to involve the chain rule. All right, so left side we have x cubed, right side we have y cubed, over here we have 6xy. So let's do the left side. Derivative of x cubed is just 3x squared, plus the derivative of y cubed at first glance is just 3y squared. But the chain rule says if you have anything but an x inside and you're taking the derivative of that with respect to x, you have to multiply by the inner derivative. So the inner function is y, so I need a times y prime there. Other side. Here I have the product rule. Now the 6 is just hanging on. We could just leave it with the x if we wanted to. So we could say this is 6x times y. So the product rule. So the product rule here says take the derivative of the first function. The derivative of 6x is just 6, multiply by the second function. And then we've got a plus the first function, 6x, and the derivative of y is y prime. So that's the product rule applied there. Next step here is I need to solve for y prime, and that's usually easier than solving for y in the original equation. So I need to put the y prime stuff together and the x stuff together. So let's see, this x squared can be subtracted over to the other side. So I am going to subtract 3x squared, and there's no like terms, so I'll put that over here. And then I want the y primes together, so I am going to subtract this 6x y prime over to this side. Okay, so what do we get? We need to put all of that together. This guy subtracts out, right? And this guy subtracts out. And then these two aren't exactly like terms, so I have 3y squared y prime minus 6xy prime equals, on this side I've got a 6y minus 3x squared. Okay, so all I did is switch sides with those two pieces. Here I can factor out a y prime. Prime times 3y squared plus minus 6x equals 6y minus 3x squared. And then finally we can divide by that. Copied that right. All right, so then that divides out. Number divided by itself is 1, which leaves just the y prime. So this is my y prime, my dy dx, my slope function. So if I then take that slope function and, well, I guess I can clean it up a little bit, right? A 3 factors out of numerator and denominator. So let's do that. New page. I can factor a 3 out of the top. Now let's write in green. Gives me 2y plus x squared. Factor a 3 out of the bottom, which gives me y squared minus 2x. And then the 3's divide out. All right, so now here's my new dy dx, my new slope function. 2y plus x squared over y squared minus 2x. And we're just going to check to see if that's actually our slope function by heading over and picking, we have already a point picked out. So here, I'm going to enter my derivative, and it's a derivative of x and y. Let's see. I think I'm just going to have to type it as is into GeoGebra. No, Desmos. I don't think Desmos can handle a function of x and y at the same time. So I'm just going to have to plug in values. Okay, back to the notebook. I'm pretty sure it won't handle that. So the point I'm looking at of tangency is 4/3, 8/3. And so I just need to plug that in there. So then the slope there, m, should be 2 times 8/3 plus 4/3 squared. So you get the x's and y's in the right spot. And then y squared, so 8/3 squared minus 2 times 4/3. Have everything in the right spots. I think so. All right, so let's type that into the computer. So I think m is a fraction, and it's going to be 2 times the y value, 8/3, plus the x value, 4/3, squared, divided by the y value squared, so 8/3 squared minus twice the x value. So that should be the slope. And let's check it. Y minus 8/3. Oops, it's not a minus. Equals the slope m times x minus 4/3, right? Oh, I missed. Darn, what did I do wrong? I got an error somewhere. There's not the slope there. Okay, so the derivative should be 2y plus x squared, 2y plus x squared divided by y squared minus 2x. Huh. I have an error. What did I do wrong? Anybody see the error? The top part has a minus. Oh, it does. I have a sign error. Thank you for pointing that out. Let's go back here. I miscopied somewhere along the way. Yeah, the numerator has a negative also. Thank you for noticing that. Good job. Rock. All right, so here, that should not be positive, it should be negative. All right, that should fix it. Thank you very much. I owe you a Pop-Tart. Nice, there we go. We got the slope. Whew. Man, that was a lot of work. All right, so implicit function theorem allows us to take derivatives of functions where we can't solve for y by realizing that y is a function of x, and we got to apply the chain rule and multiply by y prime every time a y is in an expression. Whew. All right, so we are out of time for fun with math. Sorry, I went a couple minutes over with that mistake there. We'll do more fun math tomorrow. Adios.